How do you calculate injection capacity? Calculating injection capacity, or the amount of material that can be injected into a mold during the injection molding process, is an important safety factor in the design and production of molded parts. It helps determine the size and shape of the mold, as well as the size and type of injection molding machine needed for the job. This article will discuss the steps involved in calculating injection capacity and provide tips for optimizing the injection molding process. Determine the volume of the part to be molded. First step in calculating injection capacity is to determine the volume and melt densities of the part to be molded. This can be done using computer-aided design (CAD) software, or by manually measuring the part and calculating the volume. As picture 1 shows, 49,018.2193 centimeters. It is important to be as accurate as possible in this step, as even small differences in volume can have a significant impact on the injection capacity. Determine the material density. The next step is to determine the room temperature density of the material to be injected. This is important because the capacity of the injection molding machine is typically measured in terms of the volume of the material it can inject, rather than the runner part weight. The density of the material can be found in the material data sheet or by consulting with the material supplier. As picture 2 shows, we choose the ABS material, and the density is 1.06 g/cm. Calculate the injection capacity. Once the calculating shot volume of the part and the density of the material have been determined, it is possible to calculate the injection capacity using the following formula. Injection capacity, G, is equal to part volume, cm, material density, g/cm. For example, if the volume of the part to be molded is 49,018.2193 centimeters and the density of the material is 1.06 g/cm, the injection barrel capacity would be 384, as picture 3 shows. Choose the right injection molding machine. A theoretical injection capacity is equal to injection molding machine barrel cross-sectional area multiplied by screw stroke. Injection weight is equal to injection capacity multiplied by melt density of raw materials multiplied by injection efficiency coefficient. A theoretical injection shot weight less than or equal to 80% of ABS theoretical injection capacity. So, the right injection capacity of the injection molding machine equal 394, 80% greater than or equal to 480 gram. Determine the injection pressure and speed in addition to the injection capacity. It is also important to determine the injection pressure and speed that will be used during the injection molding process. These factors can have a significant impact on the quality and accuracy of the final injection molded parts. The injection pressure and speed can be determined by consulting with the injection molding machine manufacturer or by performing tests on a small scale. Consider the cooling time. Another important conversion factor to consider when calculating injection capacity is the cooling cycle time of the material. Different materials have different cooling times, and it is important to ensure that the material has enough time to cool and solidify before the mold is opened. If the material is not given sufficient cooling residence time, it can result in defects or other issues with the injection molded parts. Optimize the injection molding process. There are several ways to optimize the injection molding process to maximize efficiency and reduce waste. One approach is to use a smaller injection molding machine, as this will reduce the amount of material required and reduce the overall cost of the process control. Additionally, using a higher quality material with a lower shrink rate can help reduce defects and improve the accuracy of the injection molded parts. Conclusion. In conclusion, Calculating injection capacity is an important step in the injection molding process. It helps determine the shot size and type of injection molding machine needed, as well as the injection pressure and speed. By optimizing the process and considering factors such as material density and cooling time, it is possible to produce high quality, injection molded parts efficiently and cost effectively.